Three.
Hello, I'm John Sciacca, and Bruce Manchon and I are going to be conducting this presentation here, which is, this is what Warhol Geophysics can do for you, and it's an introduction to our webinar series. The webinar series is 6 webinar sessions that's being provided by the NWRA. And we'll go into more detail about that in a little later. So what we're going to do right now is just go over some examples of applications of Warhol geophysical logs. And we will have Q&A later as this session is pre-recorded, or this presentation is pre-recorded. So if we go on to the next slide. Again, I said I'm John Sciacca. I'm a senior associate hydrogeologist. I work for Wood, E&I in Reno and Sacramento. I have a master's in geology, but probably most importantly, I've had 30 years of professional experience with geophysical logs and CPT interpretation. And I was the former director of the USGS Nevada Water Science Center, so I know a little bit about Nevada hydrology. So if we go on to the next slide, Bruce will introduce himself.
Hi, I'm Bruce Manchon. I'm a senior hydrogeologist with Janelle Environmental Solutions out of Boulder, Colorado. And like John, have had about 35 years of experience working with geophysical logs, also with CPT interpretation. My first job leaving Boulder here was with a small little company called Schlumberger. So I've been on both the front end of recording the logs and also utilizing it. John and I have been done these workshops and short courses for both basic and advanced Warhol geophysical applications. And we're looking forward to doing this presentation to you today. And please jot down your questions, and we'll look forward to talking about your questions at the end of the presentation. Simple basic operations of Warhol geophysics is you set up with a truck or some sort of tripod up on surface. You're running your cable down your borehole, and remember, this can be both cased and open hole. Different tools, different processes for recording in the different environments. Coming downhole through your various lithologies, you have down here your sound. And in this case, we're looking at a dip meter that's recording the dip of the formations. And in this case, we usually recommend that you always run a down log. But with this, where you have to have the caliper open, you only run this as an uphole, going uphole. Our information is recorded. Basically, you have two-way communications from uphole to your downhole sound, where your information comes back up a cable. And that can be either coming up 1 or up to 7 conduits. And that comes through your processor and then into your data recorder and into your log. As I just said, this can be very simple. Here's your data recorder. Here's your winch with your cable coming out off this through the sheave down the borehole. Or you can be large, Schlumberger here with a full operations and a larger derrick in this case, coming across your sieve and down the borehole through here. Main uses of logs, and they're numerous. It's basically only controlled within your imagination. You can identify transmissive or water producing zones, evaluate the occurrence and distribution of aquifers and aquitars. You can plan well systems, both investigation and remediation. You can assess water quality. You can assess well construction. It's also going to help you for looking at the integrity of historical wells out there, looking at well workovers and rehab, and also moving toward well abandonment.
So the logging suites, or the types of output that you get, are basically a strip chart, which shows different properties measured by the logging tools with depth. And the output can be very, very simple. Here, what you're seeing is that there's two curves. One is the spontaneous potential, or SP curve, and the other is a single point resistance curve. And this is a very simple format. And actually, these logs are very useful for identifying potentially transmissive units where there's an increase in resistance and and a negative SP deflection. So one thing that's important as you walk away from this presentation is you always really want to have at least 2 logs for interpretation. Now the next slide is going to show you a little bit more of a more complex output and log suite of multiple curves, including a gamma ray, some resistivity logs, and then also what you're seeing towards the center in the color is both a optical televiewer and also an acoustical televiewer output. And then on the far side, way over in the far right, is actually a flow direction rose that's generated actually from a colloidal borescope. So this is a more complex output with multiple curves and that you can look at things together. Of course, the more data and information you want to have provided, the more it's going to cost you. So the next slide. One other thing when you come away from this presentation, also from our webinars, is that in the case of any uncased holes, you need to run at least 1 caliper, if not a couple of caliper curves. And what you're looking at right here is a hole that is supposed to be, the drill bit was about 9 5/8 inch in diameter. The lower portion of the hole below about 225 feet is relatively engaged. But what you're seeing above that are several washouts, the one at 200 feet, and then there's a very large washout right there sitting there right around 50 feet, which is affecting the natural gamma curve. It's showing very low gamma ray reading, but that's because it's reading mostly the drill mud. So remember, always run a caliper if you're going to run open hole logs, and you want to make sure you're checking those against your curves. The other thing that's shown here is a drift of the borehole. And I give you an example, all boreholes are normally straight, which is a fallacy. This happens to be deviated as much as 20 feet down on TD near 725 feet. So next, there's even more on directional.
And as John mentioned, we really want everybody on every open hole and even case holes to run the caliper. We also want to see on every open hole a directional survey. And this is a very important when you're looking to run your casing in the hole and then following that up potentially with running a pipe or your pump down hole. So in this case, you can see here from running this directional from center, you can see this hole starting to corkscrew and then really starting to walk out. So somewhere right around 400 feet, you can see this hole is now kicking way over. And it's kicked so far over, your total depth, driller total depth is 960 feet, but your true vertical depth is like 867. So you're about 100 feet off total depth. And more important, you're off in a horizontal plane, off by almost 200 feet. What becomes interesting if you try to put this well right close to some sort of property line, in case this one crossed over into the neighboring property. So they're going to have a lot of problem right through here, putting pipe, not only running your casing through here, but this little dog leg here of running your pump down hole. So what we like to do is talk about borehole geophysics, but instead of going to the details about each log and the pros and cons, we like to showcase that in 5 case studies. We'll be talking about 2 case studies in Nebraska, 1 in California, 3 in Nebraska, 1 in California, and 1 in Nevada. So first, we're going to talk about water quality. This is a site in western Nebraska where the local municipality wells were starting to see their arsenic increasing above the MCL of 10 parts per billion. And it looked like they were constantly climbing each quarterly sampling event. So basically, we decided we needed to go in there and to see how can we isolate or protect the water quality at this site. And part of that effort, through that, we would evaluate all the existing wells, all the municipality wells, and there are 4 out there at the site. We're going to do that with test holes. We're going to also look at the driller logs of those holes and also construction detail. We're going to run test holes and then run borehole geophysical interpretation, then provide a total hydrogeologic assessment of the area. And what we found through the initial phase of looking at the existing well construction, we found poorly constructed wells. And as this schematic on the left here shows, is the design was to have the screen down here in the lower horizon, but in essence, it came along and not only screen crossed multiple horizon aquifers, there was no annular seal screening up shallower aquifers. So basically, you had a fully commingled well out here. This is the as-built that we found for one of the wells. So you can see that well was screened from 25 to 140 feet, commingling these various, and you can see from the resistivity logs, various resistivity through these three horizons. And this is the Ogallala, A, B, and C. So from that historical data, we also saw the seals, and then from our gamma ray data, it did not confer in this hole, it did not match. Neither did the well screen. We also then, after looking at all that data and all the geophysical data we ran cross sections. So as I mentioned earlier, zones A, B, and C are your Ogallala Formation. Zone D is your Pierre Shale. And you can see the sands are fairly laterally continuous, but the water quality changed. And the way we can tell the water quality is through the resistivity logs and the SP. The higher the resistivity, the cleaner or the fresher the water. The lower the resistivity, the more saline, the lower the resistivity. And we'll talk about that in another case study. So the cross-section shows those three zones, A, B, and C. We have fairly strong curve responses in the sands and weak responses in the clay. The driller logs did not show the detail that we showed in the borehole geophysics. What we did pick up was extensive weathering of the formations because we also recorded and did logging of the drill cuttings. And basically, the key thing to isolate the horizons, we had to do more look at the efficiency of the aquitard between the three different zones. So we ran pump tests through our various test holes, and doing a pump test through our various screens, we found even when we would pump on this well, it was almost instantaneous response in the nearby wells. So we knew everything was commingled through these different municipality wells, and we're going to have to isolate. And our isolation was by looking at the geophysical logs and then looking at your gamma. So we're looking right here, and right here, where we've got a good gamma ray showing a good clay that would isolate from our surface. It was more than 10 feet. So we came across here and we did a perforations in the casings of the municipality wells, and then we squeezed cement. And and you can see this to isolate this from the surface sediment from zone A, and then we also wanted to separate out zone C. After this work, you can see here the arsenic levels have been climbing. Well, after our perforation and our grouting operations, we can see our numbers just drastically decrease where we isolated the zones. So what we found was basically our cost. If we had gone with a rehab, which cost about $60,000, far less money than going with a full water treatment or drilling new wells, which would have added, $5 million and also additional operating costs. Whereas we did this with simple rehab by doing our homework, finding the number of zones to isolate, what type of casing material we had, and we also need to decide whether it's either reline or perforate. And so basically we saved this city, a substantial amount of money, and we got their water quality back.
So now we're going to deal with a case study in the East Sacramento Groundwater Basin, which is all, clastic deposition, predominantly Pliocene to Pleistocene in age. And we're going to talk a little bit about electrophases analysis and hydrogeologic conceptual site model development. A hydrogeologic conceptual site model forms the basis of all further hydrogeologic analyses that are conducted for your site. And also that includes, numerical groundwater modeling. We'll go to the next slide. One of the things that's key is you need to generate cross sections that are both along depositional dip and depositional strike. And a lot of people want to first just start connecting sands when they start to generate their cross sections. But in reality, the best thing to do, if at all possible, is to first do a correlation section with your various borings. And what you're seeing right here is a correlation section developed by the USGS based off of high natural gamma horizons, which correspond to either shales or an ash bed. An ash bed is a really great time equivalent stratigraphic marker that you can use. And they're doing this, they're hanging it there irrespective of the actual elevation of the unit. So that's one way of doing things. We're going to show you another one now as we move forward. And what we had here was a site where there was a stacked channel sequence. There were gravels, which is shown as zone A here on this cross section. And you'll notice if you look at those logs are single point resistance and lateral resistivity logs. And when you look at zone A, you see this sharp base, and then you see increasing resistivity towards the top, and then a relatively sharp top. The bottle brushes represent well screens from various monitoring wells, and there was concern about whether if there was any contamination in this unit, zone A, and also if, it had been used also as a water supply. So even for, municipal facilities. So let's go on to the next slide. And the characteristic log curve shapes that you see here from an SP curve, resistivity curves would just be the mirror image of that. And they are representative of the deposition that occurs in that sand body. The funnel that you see here at the top is indicative of less dispersed clay as you move upwards from the base of the unit. That's a coursing upward sequence in that sand or gravel body. The bell is the opposite. The bell shows relatively low dispersed clay and increasing clay towards the top. And then the cylinder is uniform deposition from the very bottom to the top or top to bottom, either way. So that process, or those shapes, are indicative of process. So if we go to the next slide, what we'll see is that in the case of the lowermost example, the bell shape is an example of lateral accretion, and that's usually common to point bar deposition associated with fluvial depositional systems. The funnel, on the other hand, is usually indicative of progradation, where there's been a very sharp or change in base level, downcutting or flooding of coarse grain deposition in response to lowering of base level, which happens in some braided or mixed load systems. And then the top one which is a cylinder, is usually a representative of aggradation, which you see a lot in braided river systems where channel bars get choked off and they anastomose and deposit vertically over time. So we applied this into our next, into these key electrophases, and this is zone A. On the left side, you're seeing a SP and then a 16-inch normal curve and a single point resistance. On the other log to the right is natural gamma, and then that's a guard resistivity log on the far right track. The guard log you see shows a very key electrophases for zone A with a sharp bottom, increasing resistivity towards the top, and then a sharp top. And we look for these electrophases, and the electrophases there are examples in the literature, from various universities and other authors, and we applied that in correlating this unit. So let's go to the next slide. What you see here was the original cross section, but what we did is go back in. First, we wanted to note or draw in where we thought we saw those electrophases before connecting the lines. And that's what we did here. And then we connected the lines. And this is a strike section looking up dip. depositionally. So let's go to the next cross section. This is a correlation cross section that's looking perpendicular to the cross section you saw before. And if you look very carefully, you'll see that zone A, the electrofacies, is repeated in each and every of those borings. These are stratigraphic borings that were strategically located about a distance of about two and a half miles. So we also hung the correlation off the base of the unit because the base represents an unconformity that was an erosional point in time where erosion occurred all across the basin into these overbank deposits. We then tied this, as we see on the next slide, to a depositional model that's in the literature, which is from Galloway and Hobday, which is a text called Turridge's Classic Depositional Systems. We determined that zone A was indicative of the bedload depositional system that's shown there, where a lot of the deposition is from bedload coarse grain deposition. And in contrast to that is the lower one, which is suspended load. And that's more indicative of what some people think of as a highly sinuous meandering river. But again, we saw what we thought was a very coarse grained braided river system. So the next slide, the original cross section I showed you, or I mean the one that's a strike section, ends about almost halfway on this page. We then had to move further down dip, and we generated these cross sections almost in a fence or a grid. I'm just showing you one as an example to be able to tie everything together. But zone A got renamed Unit B, just so we could confuse you more. But the basic electrofacies we could see as we moved further down dip off to the left, the base of the unit, we saw usually a sharp base, increasing resistivity towards the top, and then a sharp top. And this correlation is about over 4 miles in lateral extent. So we tied that together, and with our next slide, we always want to do a check. So we did a structure contour map on the base of the unit. If there's an area where the structure contours are really jammed together, then there's a problem. Usually there's some sort of structural discontinuity or there's a problem with your correlation. On the other hand, if they're really far apart, there may be an issue too, where all of a sudden there's a big gap. In this case, they actually fit very well. And the crenulated sort of shapes you see in the curves of those contours really are indicative of scour on the base of the system, which really kind of match up very well. And the gradient of that surface, essentially, or dip of that surface, was basically equivalent to what was shown in the literature for the basin, for the various units in the basin. So next slide is our conceptual hydrogeologic model. You see Unit B there, which used to be called Zone A. You notice that it's dipping much steeper than the water table and the potentiometric surface. So over on the right side in the east, there, it's in the vadose zone. As you move a little further, you'll notice that it becomes a water table unit. And then as you move all the way over towards the west, it becomes confined to semi-confined. So we were able to use this to also position injection wells, which actually had very high injection rates, as well as dealing with extraction wells. But it worked out. This thing, correlations tend to held together, and it was very well received as far as its overall technical viability. So the next slide, I think, is another study.
Now we'll move back to Nebraska to Crow Butte, where that's a uranium mining area. And part of this case study was utilizing Warhol Geophysics for their aquifer exemption. They were trying to expand their in situ leaching extraction method on the at the basal Chandran ore body. So they're looking to take it from this zone right here, and they want to extrapolate and get their new petition so they could start mining up in this area up in here. So what we need to show whether how well that extrapolates, and whether this Chandran ore body also extends up into here, and whether it's feasible economically to develop. So out in this area, they had all sorts of geophysical logs run as part of their mining exploration, numerous wells. So we took the known area down here, and then we extrapolated it up into this expansion area right here. We created various cross sections through these different areas. But the most important part, we want to bring the picks that they use down here, made sure we brought up the picks up into here. So it's very important for correlations to identify the proper marker beds, as John had mentioned over there in the Sacramento example. And then we also, what we would call is tying loops. Once we've kind of developed our cross section along here, we use an intersecting well for those correlation points, come across here, and then we have a new line. And we want to make sure everything ties together. So this is what we got. So when we came out to this, to do this investigation, this is what we got for the logs. These are called strip logs. We had no header information, no really scaling information, just what we would call these squiggly lines, and we had to come along and interpret it. Luckily, we had a lot of the drilling logs and also extrapolating from that known area. We were able to pick up where the Bureau Shale was, the Chandron, and more important, when I'll go to the next slide, the detail down in here to the mining horizon, and all this sits on top of the Pierre Shale. So this is an expansion, a blow up of that earlier log, and what we found here is the classic signature of uranium mining is very, very big gamma ray hit. Not necessarily much change in your resistivity, but the gamma ray hit was huge. And then the indication from the logs, both gamma ray and the resistivity logs, indicating the top right here of the Pierre Shale. As John mentioned, we found this to be our good point to hang our logs. This was a known point. And then it tended to be a known point here, the top of the basal Chandron, where this gamma ray had that uranium hit. From here, we built our conceptual site model and also started correlating our logs around from that lower horizon, that known area, and bringing up our cross section. Here's our basal Chandron and bringing that up through these from south to north here. As I mentioned earlier, we had our tie line to make sure all our correlations were totally wrapping together. From there, we may put our picks. So each one of these different colors represents, and there are about 4 or 5 more spreadsheets showing the various lines with the various picks at the various horizons. From that, we went to the upper Chandron and drew an isopack of that, just that unit right there. And as John mentioned, we wanted to make sure our picks were all looking good and making sure the contours made sense of the thickness of the upper Chandron there. However, we moved past that because we had such a strong database. We put this into a modeling program, a 4DM modeling program that now allowed us to really visualize our units. This lower one, this one here in orange, is the Chandron. And what's interesting as we come across, we've got a big change from this horizon up to this horizon. What we found out here through this investigation, there was a fault coming through this area, which created a little bit more interesting work for the client for the exemption moving forward. But we came across right through here and we showed where the new Chandron was for their mining. A different way of looking at it, a little twist of that picture. We now also show our various cross sections that went into creating this 3D visual. From here, we could see where all our lines were. Now we can start rotating it from a bird's eye view to now kind of looking at it from the side. And you can really see how your Chandron and your Bureau formation hang in there. So you can see your fault doesn't cross all the way to surface. From here, this went to petitioning, and that was the end of our involvement with this project.
So because this is a Nevada Water Resources hosted conference, we thought we'd probably do a little something on some characteristic Nevada lithologies, well, relative to log response. So that's what we're going to talk about right now. So we go to the next slide here. there was a study that was conducted by the USGS in the eastern portion of Nevada, and looking at several of the basins. They composited logs from the Nevada Bureau of Mines and Geology, probably oil field logs. They wanted to develop configurations for understand the basin geometry of the intervening basins in this portion of the basin and range. So there were several logs that had been run, and we're going to take a look at those in just a minute. Let's go to the next slide, though. This is a general block model of the basic conceptual Nevada hydrogeology, where we have intervening mountain ranges that are separated by basins or grabens, and the material that's eroded off of the mountains forms what is called basin fill. And there's some of the bedrock is relatively permeable and some of it isn't. So in the case of looking at hydrogeology and groundwater, obviously a lot of folks target the basin fill, but there's also a very extensive Paleozoic regional carbonate aquifer that extends from Utah across the central portion of Nevada all the way down to Death Valley and the Death Valley flow system. So we're going to take a look at a couple of those formations. The other one we're going to look at is the Chainman Shale. Chainman Shale is essentially it's a Paleozoic shale. I think it's Devonian in age. It's marine in origin, and it is a source rock for a lot of the petroleum fields in Nevada. Although there's not a lot of petroleum fields, there are a few, particularly around the Railroad Valley area. And if you look at this section here that's shown for this particular well, you see that there's basin fill at the top and volcanics, and then there's limestones, which are part of Paleozoic systems, and also the Chainman, which sits around 7,000 feet in this case, and then lower Paleozoic carbonates, which are below about 9,000 feet. So these logs here, just so you understand, if you look at the top, the acronyms, you may not know what they are. I think the one that probably people have a question for is the ILD, which is a deep induction resistivity tool. So it's measuring resistivity. Lateral log, deep, same thing. And then DPHI is a bulk density or gamma-gamma density derived porosity. NPHI is neutron derived porosity. Rho B is the bulk density from the gamma-gamma log. And then delta T is the inverse of the travel time from a sonic log. So what you notice really at the onset is that looking at the Chainman Shale and looking at the gamma ray, you see some spikes in the Diamond Peak Formation, also Chainman. That may be due to phosphatic members in the Chainman and probably some ash beds or tuffs in the Diamond Peak. Notice the gamma ray is very low in the underlying carbonates, which is very, very typical. So it's not showing much of on the other hand, the resistivity in the shale, in the carbonate, in the ILD log below about 8,000 feet is very high, which is very characteristic of carbonates. Also, when you go to both porosity logs, you'll notice the porosity in the carbonates is very low. Now notice in the case of the Chainman, the neutron porosity, which is sitting around 7,000 feet, is very high. And that's because the neutron log essentially is reading the amount of hydrogen that's in the bound water in the shale. So it's very indicative of shales to see that. And then lastly, the delta T is very, very low in the carbonates, both in the Ely limestone and the underlying formations below 9,000 feet, because they're very dense and the sonic waves travel very, very quickly. So we go to the next slide. This is an example from the White River Valley, and notice we're seeing some somewhat similar responses. Oh, the CILD at the top there is a conductivity curve from an induction log, and all the rest of these we've explained before. Notice that the natural gamma at around 8,000 feet is showing some spikes in the Chainman. And what this may very well likely be is that there may be some phosphatic members or horizons or beds within the Chainman Shale. Phosphate gives off a very strong natural gamma signature and actually can be used to develop type logs for phosphate deposits. In the case of the resistivity log, which is the LLD, notice that the shale is very low in resistivity, and the conductivity is very high because shales are electrically conductive. And then if you look at both the density and neutron porosity, notice that in the Ely limestone, they're both relatively low, sitting around, 5,500 feet. Also, that corresponds to a relatively high bulk density for the rho B curve, and the delta T is low, meaning it's very dense. So if we go on to the next slide, this is an example here where the Chainman Shale is much shallower. If you look at the caliper log, you'll notice something, that as they got further down in the drilling deeper, they used a smaller bit. And that's very common when you're going to be drilling in relatively dense carbonates, because they're very resistant to drilling. So the smaller the hole, the easier it is to actually make hole while you're drilling. The natural gamma, if you look here, starting around 4,500 feet, notice it's pretty high, and that's probably another phosphatic member in the Chainman Shale. When you get down into the carbonates below around 6,500, you'll notice that both the density and neutron porosity are very low. So if you go to both those curves, and notice starting around the Simerson dolomite, all of a sudden the rho B is even higher. So it's some of the highest of all the various units there, which corresponds to very dense carbonates, which basically agrees well with the delta T curve, which is very low, suggesting a rather dense formation. So you see how you can use these logs in part to help derive some indication of the various lithologies that you're dealing with out there within Nevada or anywhere else in the United States for that matter. And it's a pretty effective tool. So I think we have another example on the next slide.
All right, now we're going to look at water quality evaluation. Basically, you can use both. You can get a qualitative impression of your water quality and quantitative. In this case, this is a test hole. I want you to, where we've got the in red is your gamma ray, and in the green is your SP. What we're seeing over here, these are your 4 resistivity curves from normal various depths of investigation, normal logs. What's really intriguing is this bottom horizon is so much higher in resistivity than this zone right here at about 100 feet, and then this zone down up here around 75 feet. You can definitely see a different resistivity, which would imply to me a different water quality. Remember, the fresher the water, the higher resistivity. And the reason then you want to think, okay, is the resistivity tied at all to the lithology? As John was pointing out, the harder the formation, the higher the resistivity. But now we look at our gamma ray. And the gamma ray across all those horizons are the same, implying basically the same lithology from 150, let's say, all the way up to 75 feet. One thing to look at, and we'll go here in a second to look at the SP curve, which I didn't talk about. But one thing you try to do, whether it's gamma ray or SP, you try to establish, look where your clays are. And where that clay is, you establish your clay baseline. And anything breaking to the left in gamma ray indicates something a little bit cleaner, not so much fines and clay, is more sandy. Or in a gamma ray case, if it breaks to the right, as we showed in the earlier example, is indication of uranium. However, here with the SP relates to resistivity of the water in the formation versus the mud filtrate from the driller. As we log up here in sand C, there's no deflection off the baseline. We knew this was a sand because of the gamma ray, but that's telling us the resistivity of the formation water equals the mud filtrate. Coming up here to sand B, it's breaking to the right, which now is telling me the resistivity of the water is fresher, not fresher than the mud. So this is a higher, cleaner water. whereas it comes up here to sand A, it's breaking to the left. It's telling me it's more salty than the mud filtrate. So when we're looking at that log I previously described, we're looking at the three various horizons of this resistivity, seeing the same gamma ray. And as we pointed out, on the gamma ray, we created a clay baseline. We also kind of worked out where the clay baseline was also the same for the SP. Well, as we come up, our SP is way to the right of our clay line, which would indicate our formation water is fresher than our mud filtrate. And then as we move up right here around 110, 115, we've gone a little bit fresher water into L saline, and then it flips. So this unit is now saltier than the mud filtrate, and the same with this horizon. So qualitative, we can look at this well right away and see which ones are better water zone. We end up finding we had to isolate this zone from these other zones to get the client cleaner water. And again, part of the problem was the client in the municipality well at this site, we basically had a screen that came across the lower horizon, which was all right, but we had a gravel pack now that came across B into A, and then we had a kind of endless up here. So we came through here and perforated and squeezed out this area to isolate A from B, and we got the client better quality water, except for we lost on the quantity of water, but they are appreciative on the better water that they got.
So I think everybody's looked, and you can see so far just from these examples, and bear in mind that we just started to peel the skin off the onion as far as examples of applications of geophysical logs. But you can see the geophysical logs are very, very useful for subsurface imaging and also key for subsurface interpretation. They're a fraction of the cost of having to replace a well or making, poor decisions, as Bruce has shown, relative to how you complete your wells. So bear that in mind, because if you we're hoping that you'll sign up and show for our webinars, because I think you'll wind up learning a heck of a lot more about how these work.
So one final thought that I like to, John and I mentioned earlier, the importance of running caliper and potentially directional surveys. We also highly recommend that you log your hole all the way to surface, because in this case, a lot of people will stop their logging run right here at the water table. And we can see here at the water table, which is typical, our resistivity curves, because now we're in the Vado zone of air, the curves just all break to the right, and we lose our signature of SP. But in this case, we kept logging up the hole, and all of a sudden our curves came back on. And then came back on where now we can see in a gamma ray, we had a sand here with a higher resistivity. What this ended up to being was a perched layer that we detected ran a monitoring well in it that ended up being the source of our impact down to the lower horizons. So we came to all the wells here and perforated and isolated this perch zone from our water wells, our producing wells down below here. So as John was mentioning, we've got, hopefully you can join us where we can go more in depth on these subjects that we kind of very quickly, and I apologize how quick it was, but we can go more detail in on these 6 various subjects.
And what we'll do for each of these seminars or each of these webinars are set up to build on your level of knowledge. So we cover things like how the logs, how they work, what are some of the limitations of the logs and how they can be applied. And we build on that successively with these webinars where we're actually using the logs together. And the other thing I want to point out, though, is for webinars 5 and 6, 5 covers cement bond logs, which is a very, very important aspect of what we deal with as far as being able to isolate transmissive zones and also make sure that we have valid or useful and, how should I say, cement seals of, good integrity, the way that they're supposed to be. So please bear that in mind. We hope also our sessions, right now you're getting a pre-recorded presentation. Our webinars will not be pre-recorded. They will be live and they will be interactive. That means that our audience and our attendees will be able to ask questions while we talk and present the information. So we look forward to having you there if you're interested. And with that, I think we are going off time for questions.
Thank you all very much and look forward to your questions. Remember, all questions are good ones.
Yes, they are.